Just imagine being able to harness the entire energy output of a star. It sounds like something out of science fiction, right? This is exactly the fascinating concept of Dyson Spheres, a grand vision that could redefine the future of civilization. To understand the significance of a Dyson Sphere, we first need to delve into the Kardashev scale, a theoretical framework for measuring a civilization's technological advancement based on its energy consumption. The Kardashev scale is divided into 3 types, each representing a different level of energy mastery. A Type 1 civilization, also known as a planetary civilization, has the capability to harness and store all the energy available on its home planet. This includes not only fossil fuels and renewable resources, but also the ability to control and utilize planetary scale phenomena like weather or earthquakes. A Type 2 civilization goes a step further by capturing and using the energy of its entire star. This stellar civilization would have access to energy on a scale millions of times greater than what we currently consume, potentially through colossal megastructures like the Dyson Sphere. The leap to a Type 2 civilization is monumental and would mark humanity's transition from planetary to interstellar beings. At the pinnacle of the Kardashev scale lies a Type 3 civilization, capable of harnessing the energy of an entire galaxy. This galactic civilization would wield unimaginable power, able to manipulate and control the energy output of billions of stars. Such a civilization would be far beyond our current understanding, operating on a scale that could span thousands or even millions of years in the future. So, where do we stand today? Well, according to estimates, humanity is currently at approximately Type 0.72 on the Kardashev scale. This means we have yet to fully utilize and control the energy resources on our own planet. However, our energy consumption has been steadily increasing as we develop new technologies and expand our industrial capacities. The transition to a Type 1 civilization would require us to vastly increase our energy production and consumption, moving towards more sustainable and powerful energy sources such as nuclear fusion, space-based solar power, and possibly even the manipulation of planetary-scale processes. The path to becoming a Type 1 civilization is not without its challenges. It'll require significant technological advancements, global cooperation, and perhaps, most critically, a shift in how we manage and distribute energy resources. But the rewards are immense. As we progress up the Kardashev scale, the potential for technological innovation, economic growth, and societal advancement expands exponentially. Looking further ahead, the idea of a Type 2 civilization and the construction of a Dyson Sphere becomes a tantalizing possibility. The Dyson Sphere represents not just a feat of engineering, but a vision of what humanity could achieve if we can overcome the limitations of our current technological and social systems. It's a symbol of our potential to become an interstellar species, harnessing the energy of the stars themselves. In 1960, physicist Freeman Dyson proposed a concept that has since become one of the most fascinating ideas in theoretical physics and astronomy: the Dyson Sphere. Dyson speculated that an advanced civilization seeking to meet its ever-growing energy demands might construct a massive structure around its star to capture a significant portion of its energy output. The idea was born from the realization that as civilizations advance, their energy needs will inevitably surpass the limits of their planet, pushing them to look outward toward their star. The Dyson Sphere, as originally conceived, was imagined as a solid shell completely enclosing a star, capturing nearly all its energy output. Such a structure would be truly colossal, far beyond anything we can currently imagine building. However, the solid shell version of a Dyson Sphere presents numerous physical and engineering challenges, not least of which is the immense structural strain that would arise from such a vast construction. As a result, the idea has evolved into several more feasible variations. One of the more practical concepts is the Dyson Swarm, which consists of a vast collection of satellites or solar collectors orbiting the star in a dense formation. These satellites would work together to capture and transmit the star's energy back to the civilization, offering a more flexible and scalable approach compared to a solid sphere. The Dyson Swarm also allows for incremental construction, where new satellites can be added over time, gradually increasing the energy collected. Another variation is the Dyson Ring, or belt, which involves a ring-like structure orbiting the star at a fixed distance. This ring could be a simpler and less resource-intensive alternative to a full Dyson Sphere, though it would capture only a fraction of the star's energy. Still, even a fraction of a star's energy output would be orders of magnitude greater than what any civilization currently consumes. The Dyson shell, often conflated with the original sphere concept, is a more theoretical version where a hollow sphere encases the star. This design, while intriguing, is widely regarded as impossible with our current understanding of materials and engineering due to the enormous gravitational forces and the need for materials of extraordinary strength. Lastly, there's the Dyson bubble, which envisions a collection of satellites held in a stable orbit around the star by balancing the star's gravitational pull and the radiation pressure from the star's light. This concept shares the advantages of the Dyson Swarm with the added complexity of maintaining the precise balance required to keep the satellites in place. Building any of these structures would be an undertaking of unprecedented scale and complexity, requiring materials and technologies far beyond our current capabilities. To understand the magnitude of this challenge, consider the material requirements alone. A hypothetical Dyson Sphere, constructed of steel, would require an astronomical amount of material. For example, even a thin shell with a radius of 0.25 astronomical units, AU, and a thickness of just 1 centimeter would require more steel than could be mined from dozens of Earth-sized planets. The logistics of mining, transporting, and assembling such vast quantities of material are staggering. The engineering challenges are equally daunting. Supporting a structure of this size would require breakthroughs in material science, energy transmission, and space construction techniques. The structural integrity of a Dyson Sphere or any similar structure would be constantly threatened by the immense gravitational forces involved, as well as the need to dissipate heat and manage the radiation from the star. Energy costs represent another significant hurdle. The energy required to build, launch, and maintain a Dyson structure would be astronomical, possibly exceeding the energy output of the very star it aims to harness. Moreover, such a project would likely take centuries, if not millennia, to complete, requiring a level of societal stability and economic commitment that humanity has never sustained. Potential failures add another layer of complexity. The risk of Kessler syndrome, where collisions between satellites generate cascading clouds of debris, could spell disaster for any large-scale orbital structure. Even a single collision could lead to a chain reaction, turning the orbit into an impassable cloud of shrapnel that could render the entire structure inoperable. The economic and social impact of such a failure would be catastrophic, potentially setting back the civilization by centuries. The concept of Dyson spheres, while seemingly far-fetched, is rooted in a trajectory of technological advancement that we are beginning to glimpse today. Our current progress in space technology and energy collection lays the groundwork for future endeavors that could one day lead to the construction of Dyson-like structures. Advancements in satellite technology, such as the miniaturization and increasing efficiency of solar power systems, represent incremental steps toward more ambitious projects. These developments are vital as they demonstrate the practicality of deploying and maintaining vast networks of satellites, a concept central to the idea of a Dyson swarm. Building a Dyson swarm, or ring, is far more feasible than the traditional Dyson sphere. A Dyson swarm, for example, could be constructed incrementally, with individual satellites or solar collectors gradually added to the system over time. This approach avoids the monumental challenge of constructing a single, continuous structure and allows for flexibilities in the design and deployment of the swarm. Each satellite in the swarm could be equipped with advanced solar panels to capture the star's energy and transmit it back to Earth or another central hub. The incremental approach to building a Dyson swarm is not only practical, but also aligns with our current technological capabilities. Modular construction, where smaller components are built and assembled over time, offers several advantages. It reduces the initial investment and risk associated with the project, allows for testing and improvement of the technology as it is deployed, and offers the potential for early returns on investment by harnessing energy from the star long before the structure is complete. This modular approach also enables the construction of various types of Dyson structures, such as rings or belts, which could be expanded or adapted as technological capabilities evolve. While a complete Dyson sphere remains a distant goal, the Dyson swarm presents a more achievable solution that could meet the energy needs of a future Type 2 civilization. The swarm concept also allows for scaling, meaning that as the civilization's energy demands grow, additional satellites can be deployed to capture more of the star's output. This flexibility makes the Dyson swarm an attractive alternative to the more rigid and resource-intensive Dyson sphere. The search for extraterrestrial life has also brought the concept of Dyson structures into the spotlight. In 2015, the star KIC 8462852, also known as Tabby's star, garnered attention due to its strange light fluctuations, which some scientists speculated could be caused by a large structure orbiting the star, such as a Dyson swarm. Although other explanations, such as clouds of comets or dust, have been proposed, the idea that these fluctuations could be evidence of an alien civilization's megastructure captured the imagination of the public and scientific community alike. The implications of discovering a Dyson swarm or similar structure built by an alien civilization would be profound. It would not only confirm the existence of extraterrestrial intelligence, but also provide a glimpse into the technologies and capabilities of a civilization far more advanced than our own. Such a discovery would challenge our understanding of the universe and our place within it, opening up new avenues of research and speculation about the future of humanity. Current efforts to search for signs of advanced civilization include scanning the cosmos for unusual patterns of light or energy emissions that could indicate the presence of megastructures like Dyson spheres. Scientists use tools like the Kepler Space Telescope and other observatories to monitor stars for irregularities that cannot be explained by natural phenomena. If we were to detect such a signal, it could provide the first concrete evidence of a civilization that has harnessed the power of its star. While we have yet to find definitive proof of such structures, the search itself is a testament to our curiosity and drive to explore the unknown. The potential discoveries that await us, whether they reveal advanced alien civilizations or new insights into the limits of engineering and technology, are bound to reshape our understanding of what's possible. As we continue to push the boundaries of space exploration and technology, the dream of building a Dyson swarm, or even discovering one, remains an inspiring goal for the future.